All right, this is the first part of section 6.3. We're dealing with binomial random variables. So in the last sections, we were dealing with random variables, but now we're dealing with a very specific type of random variable called a binomial random variable. And we're going to figure out, well, what are the conditions that need to be met so that we know we're dealing with a binomial random variable. We'll talk about its distributions. We'll talk about how to calculate the mean and standard deviations of those and how to interpret those. And then also we'll talk about the similarities, or when you can actually use a normal distribution to approximate a binomial distribution. A binomial distribution is discrete, but under certain circumstances, we can sort of approximate it with a normal distribution. And normally that's going to be easier to do. Okay, a binomial setting. So what is the situation that results in a binomial random variable? So some sort of random variable, and it's going to be looking at the results of a fixed number of repetitions of some chance behavior that we try again and again and again. And if that's the case, then we're going to be looking at a binomial random variable. So a binomial setting arises when we perform several independent trials of the same process, the same chance process. We're going to record the number of successes that we get in those trials. All right, so there's 4 conditions that have to be met in order for us to be know that we're in a binomial situation. So the first one is binary. In other words, there's 2 possible outcomes. And one will be considered success and one will be considered failure. We might still be doing something like rolling a standard 6-sided die, which you might say, well, wait a minute, that has 6 outcomes, not 2 outcomes. But one of those outcomes, or maybe 2 of those outcomes, will be considered a success. So maybe I roll a die and I'm looking for a number on that die that is a multiple of 3. So maybe 3s and 6s are going to be considered successes, and 1, 2, 4, and 5s would be considered failures. So somehow we're going to classify the outcomes as either success or failure. And then each outcome has to be independent. For example, if I decide to take cards out of a deck of cards, once I take one card out of a deck of cards, if I don't replace the first card, then if I take a second trial and I take a second card out, the outcome of the second card draw is going to be dependent on what happened the first time. Like what card I took out first is going to have an influence on the second card. And then what I took out the first and second time is going to have an influence on what comes out the third card. So if you're using something like a deck of cards, you would have to replace the first card and shuffle before you draw out a second card. So independence, things like rolling a die, that's independent. Flipping a coin, that's independent. But you got to make sure that each trial is independent of the previous trial. And then the number of trials has to be set ahead of time. So I'm going to shoot 10 baskets. I'm not going to shoot baskets until I get one in. That's a different situation. That's a geometric, which we will talk about next class. But here we have to say, okay, we are going to attempt so many trials, and we know that up front. And then the last thing is that the probability of success has to be the same every time. So like I haven't shot a basketball in years. So the first time I shoot, I'm going to really be bad. My probability of success is really bad. But if I'm going to shoot 50 baskets, then by the time I'm shot my 50th basket, I probably will have a better chance of getting it in than I did the first time when I haven't shot a basket in years. So we have to assume that the probability of success for each trial is the same. All right, and then we have like an acronym. It's kind of a silly acronym that our book always tries to force acronyms on these things. So it's BINS is like the 4 things to remember. The B and the I and the N sort of makes sense. The S, I mean, I don't know, it really should be a P for probability of success is the same, not S, but then that would be like PINP. I don't know, it wouldn't be a word. So, I mean, not that BINS is a great acronym, but that's what the book uses. Okay, so let's talk a little bit more about the binomial random variable. Consider tossing a coin n times. So each toss gives either a heads or a tails. Knowing the outcome of one toss doesn't affect the others, so they're independent. If we define heads as success, then the probability of success, or the probability of a heads, is going to be 0.5. And then, so the number of heads in n tosses, that's going to be our random variable. That's going to be x, and so x will count how many successes. And so that x, that is going to be a random variable x, that is going to be a binomial random variable, and it will have a binomial distribution. So we talked about probability distributions for random variables in the past section, but now we have a very special binomial distribution or binomial probability distribution specifically for a binomial random variable. So the count x, that's going to count the number of successes in n trials. So this binomial random variable is going to have a binomial distribution. And when we talk about a binomial distribution, there's 2 parameters. Like, for example, when we talk about a normal distribution, the mean and the standard deviation completely defined that random variable that was normal. Here, the things that define our binomial distribution or our binomial random variable are going to be n, the number of trials, and P, the probability of success for any one trial. Now, if I'm going to attempt to shoot 10 baskets, X will count the number of successes. How many baskets do I make in my 10 attempts? And so I could miss them all. It could be 0, or I could make all 10, or anything in between. So the X is my random variable, my binomial random variable, and it will take on values from 0 up to n, the total number of trials. All right, so let's look at a particular situation here. A man and a woman each contribute half of their genes to an offspring. So let's assume that that couple has blood types such that 25% of there's a 25% chance that their children, any one child, will have O blood. Now, I'm sure some of you probably remember your biology, and you probably could tell me like, oh, that means the parents have to have this type of blood. I don't know, whatever it is. This is that, 2-way biology table with genetics, recessive and dominant genes, I think. Anyway, it's been a long time since I've taken biology. All right, so if the couple plans to have 5 children, okay, that sounds like N, right? They're planning ahead of time to have 5 children. Then we can find the probability that 2 of their children will have O-type blood. Okay, so this is, well, first of all, let's determine whether this is a binomial setting. Let's go through that BINS. All right, so is it binary? Yeah. So they either have, now you might say, oh, but there's 4 types of blood types, right? And then I guess if you talk about the positive and negative, there might be even more. But for us, it's either success or failure. So either it's O-type blood or it's not blood type O. All right, so that's, yes, it's binary for us. Are they independent? And genetics tell us that yes, each child's blood type is independent of what the blood types came before in previous siblings. Do we have a fixed number? Yes, they say they're going to have 5 children. And is the probability of success the same every time? Yes, it doesn't change. It's all based on what the parents' blood types are, and those aren't changing. So the probability of success is going to be the same every time. All right, so we'll come back to that example, but let's practice a little bit of are the situations a binomial setting. So we shuffle a deck of cards, we turn over the top card. And then we take that card and we put it back in the deck and we shuffle again. And then we repeat this process 10 times, drawing 10 cards, and one each time. And then we want X to be a random variable, and it is the number of aces observed. So is X a binomial random variable? Is bins satisfied? And so we can go through 4 things. Success is an ace, failure is not an ace. Sure, that sounds good. Replacement. So since I'm putting the cards back in, the second draw is independent of what the first draw was, and so on. So yes, we have independence, and that's because we have replacement. There's a fixed number of trials, 10, and the probability of success, the probability of getting an ace out of any time you pull a card out of a deck. There are 4 aces out of the 52 cards. So yes, that's the same every time because, again, we are replacing the card every time. So the probability is the same every time. And yes, this is a binomial situation. All right, number 2. I'm going to choose 3 students at random from your class, and then let Y be the number, either 0, 1, 2, or 3, of the students who are over 6 feet tall. So think about bins and see if that's been satisfied. All right, so the success and failure, the child I choose is either 6 feet tall, over 6 feet tall, or not. So success and failure. But the problem is for independence. This is a problem. So let's think, instead of pulling 3, so we're not replacing, right? So I'm pulling 3 students and saying, okay, you 3 students come up to the front of the class, and then we'll put a tape measure against the wall, and we'll see, are you over 6 feet or are you not under 6 feet? So, so the problem is, let's think of it, easier to think about it as being, let's pick 1 student. All right, so what's the probability that that 1 student is over 6 feet tall? Let's say half of the students. So let's say 15 of the 30 students are over 6 feet tall. All right, so the probability is 1/2. Now I take that student out of the group, and they're now standing at the front of the room. Now I'm going to go to pick a second child. That second child, the probability of success has now changed in the students that are left, because it depends on what this first student was, right? And so the probability of success, it depends on what the first child's height was. And then so that those 2 children are at the front of the room. Now I'm going to go choose a third student. The probability of choosing a child over 6 feet tall, a success, is changed again, because the population has changed. And so now if those people I picked were short by dumb luck, then that means the rest of the population has a greater chance of who's left. There's a greater chance of picking someone who is over 6 feet tall. And so this is not a binomial situation. The independence and the probability of success sometimes are interrelated. Okay, so in this case, because I didn't replace, I didn't randomly pick someone, measure them, and then throw them back into the pile, and then pick another student, measure them, throw them back into the pile, like we did with the deck of cards. So this one is not a binomial situation. All right, next one, number 3. A fair die is, so that just means that each side is equally likely to come up. We toss it 100 times. Sometimes during the 100 rolls, one of the corners of the dice gets chipped off. All right, and so now we're going to let the random variable W be the number of 5s we got when we rolled. And so is this going to be a binomial situation? So you probably are a little dubious of the fact that like halfway between or somewhere in between rolls, the chip on the corner broke off the die. And so each roll is, either going to be classified as success or failure. So that's good. Each roll is independent. That's true. We have a fixed number of trials. That's true as well. But the problem is the probability changed. So the physical structure of the die changed. And so the probability of getting a 5 probably changed as well. And that's not allowed. So we do not have a binomial setting here. All right, so let's get back to the situation where the 2 parents are going to have 5 children, and get back to the question is, what is the probability that 2 of the 5 children will have O-type blood? All right, so so you might think of this as, what's the probability that the first 2 children are a success? So they have O-type blood, and then the other 3 do not. So that would be, probability of the first child being an O-type blood is 25%. The second child, 25%. And then what's the probability that the third child is a failure? That would be 75%, and 75%, and 75% for the fourth and fifth children. So an easier way of calculating this is simply the probability of success, 25, raised to the second power, times the probability of failure raised to the third power. And so that is about 2.6% chance that that will happen. However, we don't really care where those 2 children are. Like, that probability we just show here on the screen is for the probability that the first 2 children have are a success and the last 3 children are failures, but we don't care where the 2 children are. So it's like, how many different ways can we arrange those 2 successes in the 5 attempts? And so if we look, this is how many different ways we can arrange the 2 successes. And so that ends up being 10 different ways. And if you calculated each one of those probabilities, it doesn't really matter what order we multiply the things in. In each case, there are 2 successes and 3 failures. And so this probability, the one that we calculated up above, is the same for all 10 of these all these 10 outcomes. And so what we want to do is just simply multiply the probability we came up with by 10. So because there's 10 ways in which we can get arrangements of 2 successes in 5 trials. All right, so we simply multiply that by 10, and so we can see that it's about 26% of the time. If we had lots and lots of these parents with the same genetic makeup, and these parents were all these sets of parents were planning on having 5 children, then we would expect about 26% of these families to have 2 children with O-type blood. All right, so in the previous slide, we were trying to figure out how many ways could we arrange 2 successes and 3 failures. And so this is something called the number of arrangements. So it's like the number of arrangements of so many successes in total trials. So sometimes we'll use the letter K to represent the number of successes. And so in that case, it's how many ways can we arrange K successes in N trials, all right? And so we'll talk about how we can do that. We have a mathematical process to do that. But notice we took the probability of success P and raised it to the number of successes, and then the probability of failure, which is 1 minus P, times N raised to the N minus K. So N minus K is the number of failures. Remember, N is the number of trials, minus the number of successes would be the number of failures. So it's the probability of success times the number of successes, raised to the number of successes, times the probability of failure raised to the number of failures. All right, so that's how we would calculate the probability part, but then we also need in front the number of arrangements of K successes within N trials. And so we have something called a binomial coefficient. Our calculators will calculate this. It can be written in a couple different ways. Our calculator uses this first notation. We often will use this kind of a notation, but also we can calculate it by hand, which we're not going to do because our calculators will do it, but we would use factorials for that. So if you want to, you could certainly do it by hand, but we don't need to. So n factorial, if you remember from Algebra 2, n factorial just means n times n minus 1 times n minus 2, and so on, all the way down to 1. And remember, too, that if it comes up, the 0 factorial is always 1. All right, so we'll show in an example in a minute how to do that binomial coefficient, how to calculate that in our calculators. All right. Okay, so this is the general formula. So it's the binomial coefficient, first thing, number of x, arrangement of x successes and n trials. The next thing is the probability of k successes, so probability of success raised to the k power, and then probability of n minus k failures. All right, so we are going to use our three-step process, just like we learned in the last section on just random variables when we were calculating random variables. Here, we're going to apply them to binomial random variables. All right, so the first step is going to be first define your binomial random variable. Usually we'll use X or Y. The next thing will be to say what that that it has a binomial distribution, and the binomial distribution is determined by two things: the n value, the number of trials, and probability of success for each trial. And then we'll say what the probability is that we're actually looking for. All right, so that's step one. Step two will be to perform your calculations, and we'll show you in a couple slides how to actually do that with your calculator. So that will be kind of how you'll expect to do it. You'll want to say what it is you're typing in your calculator. And then the third would be just to answer the question in a full sentence. Okay, let's try an example. All right, so let's go back to this same example of the parents who are going to have 5 children. This time, let's find calculate the probability that they will have exactly 3 children with O type blood. All right, so step one, we want to say, all right, define a random variable. So let X be, and X will represent the number of children that have O type blood. So remember that, theoretically that could take on a value of 0. They could have 0 children with O blood, 1 child, 2, 3, 4, or 5. And so that random variable X is going to have a binomial distribution. And so we know X has a binomial distribution. You need to tell me the N and the P value. And then finally, what is it that we're trying to find? We're trying to find the probability that X is equal to 3. All right, so now let's do the calculation. Here we'll do it by hand, and then we'll show how to do the whole entire thing just with our calculators. We'll try that in a minute. All right, in another slide. All right, so to do this by hand, we say, okay, it's the binomial coefficient of what we say is sometimes we'll say 5 choose 3, so 5 trials of which we want 3 successes. And then probability of success raised to the 3rd power, because that's the number of successes. Probability of failure raised to the 2 power. All right, so we have a way of calculating this binomial situation, the binomial coefficient, in our calculators. So what we want to first do is go to your home screen, clear out your home screen, and then type a 5. Then hit the math button on the left side of your calculator, and then scroll over to the menu PRB, which is probabilities. Then go down to NCR and hit enter, and then type a 3. So you type the N, you type the 5, you go to math, go to probabilities, choose NCR, you hit enter. Then you type a 3. That takes you back to your home screen. It pastes the NCR onto your home screen next to the 5. Then type a 3 and then hit enter. And that will give us 10. So that tells us that there are 10 ways of arranging 3 successes in 5 trials. And so that gives us this 10 number here. Okay. And so calculate that final value here. All right, so it's 0.08789. And so now, you can round if you want to. So you can say 8.8%, or you can say about 9%. That's fine. But in a full sentence, answer the question. All right, so there's about 8.8% probability that 3 of their children will have type O blood. All right, let's try part B then. Should the parents be surprised if more than 3 of their children have O blood? So more than 3 would mean 4 or 5. So now we've got to calculate 4 values. All right, so I'm sorry, 2 values. We got to calculate the probability that X could equal 4 or that X could equal 5. And or generally means we're going to add, so we're going to add those up. So the probability that X would equal 4 plus the probability that X would equal 5 is another way of saying the probability that X is greater than 3. So we have to do both of these calculations. You can see now it's getting pretty tedious. You can still go and use your NCR calculation in your calculator to find the binomial coefficient of how many ways can we arrange 4 successes in 5, and how many ways can we arrange 5 in 5. And so that was 5 and 1, or those 2 values. And you can see how we would do these calculations. But ultimately, I'm going to recommend that you do these calculations in your calculator. The calculator will do this whole thing, and we're going to practice that in a second. Okay? And then ultimately, I guess I didn't really do this perfectly as a this one as a 3-stepper, but ultimately, let's answer the question as we should with a sentence. So should they be surprised? And yeah, they should be surprised. The probability that they would have 4 or 5 children is pretty low, less than 2% chance. So yeah, they should sort of be a little bit surprised if they got that many children. 4 or 5 children with O blood given this situation is pretty rare. All right, so now let's show how you would do this these calculations on your actual calculator. So with your calculator, you will put the second vars button, which is distributions. So hit second vars, and this is where we were getting the normal CDF that we were using before. But this time we want to go down, and you might have to scroll down past your, bottom of your screen, past the bottom of your screen, and get to Binomial PDF. So this again is the same situation where we're dealing with 5 children. And how many children are going to have O-type blood. So we know that the possible outcomes are 0 children with O blood, 1 child, 2, 3, 4, or 5. And so we're going to fill in this probability distribution for this random variable X. But we're not going to do these calculations all by hand. We've already calculated some of them. We've already actually calculated on previous screens 2, 3, 4, and 5. But let's get our calculator to do it. All right, so we use this binomial PDF. It stands for a binomial probability distribution function. And so the first number we put in is the number of trials, n, which is 5. And then we want to put in the probability of success, which is 0.25, 25%. So as a decimal, 0.25. And then we want to put in the last value is which one of these X values are we trying to calculate. So the first one of 23.73, we would find that value by using binomial PDF with a 5, the 0.25, and the 0. So this will give us the probability of getting 0 children with O blood, assuming we're going to attempt it 5 times with 5 children, and the probability of success 25%. All right, so use that same process, changing, of course, the last number, the X value, to 1, and then to 2, and then to 3, 4, 5. So you should be able to calculate it with 1, right? Put the 1 at the end. So we get about almost 40% of the time we would expect the 40% chance that one of the children would have O-type blood. And so calculate the rest of those. Remember, on your calculator, once you do, you pick up a binomial PDF and put in your 5 and then your p-value of 0.25, and then your x, let's say you did 0, what you can do is after you've run that in your calculator's home screen, hit second enter, and it recalls the previous command that you ran, and then you can just cursor back and change, let's say, the 0 to a 1. So you wouldn't have to go, go to second vars and then change the value, hit enter, paste it to a home screen, and hit enter to execute. You could just do second enter, and it repulls up from the home screen the previous command, and you can just change that last x value to a 2, to a 3, to a 4, and so on. All right, so now hopefully you were able to get all these same values. But now let's see, this is not going to be super convenient. Sometimes if we wanted to calculate the probability of a set number of children, 1 or 2 or 3, that have O blood, then this PDF works well. But what if we wanted to ask, the probability that x is less than or equal to 3? Well, we have the numbers in front of us, so we would simply add up the probability values for 0, 1, 2, and 3, simply add those up. But assuming we don't have this table in front of us, and they simply ask us to calculate this value to start with, that would be a really tedious thing to have to go and use PDF 4 times for 0, 1, 2, and 3, and then simply add those up. That would be kind of tedious. So we have another method for doing this in our calculators, and that is using a Binomcdf. So you want to do, again, second vars, which takes us to the distributions, and go to Binomcdf. CDF stands for Cumulative Distribution Function. And so what this does is it calculates the x value you put in is for a particular value and everything below it. So if we wanted to calculate the probability that x is less than or equal to 3, then we would put a 3 in the CDF. So that will automatically calculate the probability of 3 and everything below it. All right. So let's practice some more of this on the next slide. Okay, so here, different situation. This situation, we have 6 trials, and the probability of success every time is 15%. Let x represent the number of successes in 6 trials, and x is a binomial random variable, assuming all that. Then let's find the probability that you would have 5 successes. All right, so this is going to be using a Binomcdf because we're looking for the probability of a particular value, and we put a 5 in there. All right, so you're not actually, if you're typing this in the old 83s or the old format TI-84s, you are not typing in the N and the P and the X, you're just doing the numbers. But when you write this out on paper, on a quiz or a test, you need to tell me what the 6 is, that it represents the N, the 0.15 represents the P, and the 5 is going to be the X value. All right, so plug that in, and you should get a pretty low number, 0.000387. All right, so now let's do the probability that x is less than 5. All right, so I find that it's nice to write out all the possible values. So if we're doing 6 trials, the possible x values are 0, 1, 2, 3, 4, 5, and 6. So what are we trying to calculate? We're trying to calculate values less than 5. So that what I do is I kind of circle the values I'm looking for that I want to include in my answer, and that helps figure out what value goes in the binom function in your calculator. So this is a range of values, so we're using a CDF for this, but you got to be careful. You got to use, even though this is 5 over here, we're not putting 5 in, we're putting in 4. It's the first thing that we want to include, and then everything below it. So 5 is not part of what we want to include. We would not have 5 in our function. All right, so plug that in, and you should get something like 0.9996. All right, last one. Probability that you get an x value greater than or equal to 4. So again, I'm going to suggest that you list out all the values and circle the ones you're trying to calculate. So greater than or equal to 4 would be these. We don't have a way of calculating this directly. Our calculator, our Binomcdf, will calculate the probability for a particular value of the random variable, binomial random variable, and everything below it. So in this case, we need to do 1 minus binomial CDF with a 3 in it, with a 3, because the calculator is calculating this stuff, and all of them together have to add up to 1, so we can subtract from 1, but we need a 3 in there. Okay, so that's 1 minus 0.9941, or pretty small, 0.0059. All right, so let's talk about the mean and the standard deviation of this binomial distribution. So we can make a histogram from our distribution table, from the binomial random variable, and you can see that this is definitely, the shape is definitely right skewed. You're much more likely to have 0, 1, or 2 children than 3, 4, or 5. You can see the bar is so small for 5 that you almost can't even see it. All right, so let's talk about the center, the median. That's pretty easy to kind of see that it's going to be a 1. The mean, we could calculate the mean. We can certainly take 0, the first value of x, times its probability, plus 1 times its probability, times plus 2 times its probability, and so on. But if you think about it, you're having 5 children, and you're going to have 5 children, and the probability of O blood is 25%. So you would expect about 1.25. So that kind of intuitively makes sense here. And indeed, the mean or expected value is going to be n times p. So the number of trials times the probability gives us our mean value. Now, to calculate the standard deviation, we could use the same formula that we had before with the particular x value minus the mean, and take that and square it, times the probability, do that for all of the 6 values, and add them all up, and then we would take the square root of that, and that gives us our standard deviation. However, we have a much quicker formula for the standard deviation. We don't have to go through all of that. That is the process that we would have to go through for just a random variable, but for a binomial random variable, we have a much quicker way of calculating it. And so here is the formula again for the mean that we saw on the previous slide. And here is the formula for the standard deviation. So it's the square root of n, the number of successes, times p, probability of success, times the probability of failure. So if p is success, 1 minus p is the probability of failure. And again, these only work for binomial distributions. They do not work for any other random variable distribution. All right, so this is an example. This example uses an activity that is in the book on page 346, if you want to go look at that at some point. But let's assume Mr. Bullard is a statistics teacher, and he has a class of 21 students. And let's assume he did this activity. So basically, the activity is each student is given 3 different cups, and they're trying to identify which cup has which of the 3 has bottled water in it. try to identify the other two that are tap water. And so we're assuming that the students cannot tell the difference. And so that means that they have 1/3 chance of correctly identifying the bottled water. So they taste the 3 cups, but they can't tell. So they're going to say, well, I guess it's this one. So if they really can't tell the difference, then they have a 1/3 chance of correctly guessing. So let X be the number of students who correctly identify the cup containing the bottled water. All right, so we have 21 students, so X will take on a value in this class anywhere between 0 and 21. Maybe everybody can tell the difference, or everybody guesses correctly, and so all 21, or maybe no one, right? So we would expect about 1/3 of the kids, right? Because the probability of success, you have a 1/3 chance. So if you're doing it just by dumb luck, you would probably expect about 1/3 of them, right? So we know, we just looked at the mean before. And so that's what we're really looking for, is the mean and standard deviation. So since X is a binomial random variable, we know the N is 21, we're 21 trials here, and we know the probability of success is 1/3. What are the formulas and for mean and standard deviation, and find those. Okay, so the mean is just N times P. Kind of intuitively, if everyone has got a 1/3 chance of guessing correctly, then we would expect the expected value, or the expected number of correct guesses, would be 7. And then the standard deviation. Standard deviation, square root of N times P times 1 minus P. So number of trials times the probability of success times the probability of failure, and then you'll take the square root of that. So that ends up being something more like 2.16. So how do we interpret that? This one's a little bit harder to think about. So if this activity were repeated many times, so let's say we had lots of classes of size 21 that repeated this exact activity, and everyone was guessing at the water, then we would expect that the number of correct guesses would differ from the mean, which was 7 over here, would differ from that by about 2.16. So that's assuming we did this whole activity with lots of classes of size 21 and everyone was guessing, then the number of correct people guessing in the classes of 21 would differ from 7 by about 2.16. All right, so let's I'm just going to go through an activity here that talks about replacement versus not replacement. And so suppose that a tech supplier inspects a simple random sample of size 10 of a shipment of 1,000 flash drives. So also assume, unrealistically, that we know 2% of the flash drives are defective. So 2% of them are bad. All right, we're going to let X represent the defective flash drives in our sample. So is this a binomial setting? So you think about it, the issue here is that the probability is different. When I pull one out, right, 2% of the 1,000 flash drives are defective, but as I pull them out one at a time for my sample size of 10, the probability of defectiveness is changing as I pull them out. All right, so if we look, the probability that you have no defects in the 10 that you pick out, that's what we want to look at. So the probability of no defects. So what's the probability that the first one I pull out is that works, right? So there are 980 out of 1,000 that are working. And now what about the second one? The probability that the second one I pull out, what's the probability that it works? Well, assuming, of course, the first one is working, then now there's 979 out of 999, right? So on the third, well, now 2 of them are out and they are working. So what's the probability that the next one I pull out randomly is working? That's 978 out of 998. 978 out of 998. So these numbers are changing a little bit every time. Well, they're changing by 1 every time, but the numbers are so big that it's not going to affect it too much. And notice we're sampling way under our 10%. So if I actually changed all those into decimals, you would see that this is what they are. They all are about 98%. The first ones are 98 out to 4 decimal places. They are actually a little bit different than that. But you can see it, if I multiply all those together, I get about 81.6% chance that they're all going to be working. All right, so now let's assume that this is actually a binomial setting. And we use our calculations to calculate this, assuming it's an actual binomial setting. So that would be, we're looking at no defects, right? So we want a 0 defective out of the 10. And so you can see here we have the same sort of calculation, and they're similar, right? I mean, so this number is pretty close to this number. They're not exactly the same, but they're pretty close. And so this is that whole idea of replacement versus not replacement, and not sampling too many of the population. Because if we were to sample a lot more, then these numbers would change a lot more than these would. They would be much smaller, and the probability this probability here would differ quite a bit from this one, and so then our final calculation would be a lot further off. So this is beginning that our idea of talking about replacement versus not replacement, and why we're not allowed to sample more than 10%, because the calculations will be off. All right, the binomial distributions are important in statistics when we wish to make inference about a proportion P of successes in a population. All right, so we talk about here the violation of the independence condition, and that's kind of what we were just talking about, okay? So this all boils down to the fact that we cannot be sampling more than 10% of our population. Otherwise, if we're not replacing, then we are violating the independence condition, but our calculations are not going to be off so much that we have to worry about it, so long as we're not sampling more than 10% of our population. So N, the size of our sample, should be less than or equal to 1/10 of the population size. All right, so sometimes we're going to be able to approximate a binomial distribution using a normal distribution. So you can see here is a binomial distribution. It is curved. It is skewed to the left. On top of it, I sort of have a red normal curve, so to compare. But as I increase my sample size, so my number of trials in this case, from 10, which was in the first one, to 20, now you could see that it's still a little bit skewed to the left, but it's looking a lot more normal. And then let's go and take it to even bigger. Let's go to the sample size of 50, and now we can see that that if the sample size is large enough, then the distribution, the binomial distribution, looks a lot more normal. Also notice that it looks less digitized, right? So the curve fits much tighter to those to the distribution because the class widths are much smaller. Okay. So what this boils down to is sometimes, even though a binomial distribution is discrete, a normal distribution is continuous. we can approximate a binomial situation, a binomial random variable with a normal random variable if these two conditions hold. So if n times p is greater than or equal to 10, and at the same time, n times 1 minus p is greater than or equal to 10. So if the probability is rather high, then of course we're going to be over 10. That's not a problem. But if p is really high, that means 1 minus p is going to be really small. And so then we're going to have a problem. So in order for both of these conditions to be satisfied, either n has to be really large, in which case if n minus p or p is small, then the product is still going to be greater than 10, or p has to be close to 0.5. If p is close to 0.5, then 1 minus p will also be close to 0.5. And then n doesn't have to be so big. So it's the n times p is the expected number of successes. N times 1 minus p is the expected number of failures. And both of these must be larger than 10. And then we could use a normal distribution, and normal distribution requires a mean, so we would use n times p, and requires a standard deviation, and we would use the standard deviation calculation for the binomial situations to give us our mean and our standard deviation for the normal curve. All right, let's go through a three-step example then. And so in this particular example, a particular school district claims that 82% of its seniors are attending college. Okay, the AP statistics class is going to take an SRS of 80 seniors and ask them, right, as a test to see if that 82% is valid. And so only 57 of the 80 in their sample said that they were planning to attend college. And so does this call into question whether or not 82% of the seniors go to college from this district? And so let's think about if this is a binomial setting. So the binomial situation, yes, you're either going to college or you're not. The independence, now we got to make sure that we're not sampling more than 10%. So that means in this particular school district, there would have to be over 80. Is there a fixed number? Yes, we asked 80 students. So that was the fixed number. And then probability of success. So we're assuming that the district is not lying to us. And so we're going to use as the probability of success. Every time we ask a random senior, probability that they're going to college is 82%. So that's what we're going to use until we can, until we have reasons to believe otherwise. So the first step in our three-step process is to define the random variable x. It's the number of seniors in our sample that are attending college. X is a binomial distribution. The total number of trials was 80, because that's how many seniors we asked. According to the district, 82% are going to college. So the probability that someone said they were going to college was 82%. We want to find what's the probability that we would get in our sample, 57 or less. And so just one thing, to students often when they do this problem, and they think, oh, we're going to use PDF of 57. We don't want to calculate the probability that 57 people said they're going to college, but 57 or more extreme. And so 57 out of 80 is on the low end of 82, on the low side of 82%. And so if you see, the probability that it's exactly 57 is 0.006. So what we want to do is we don't want to calculate that one. We want to think about this as, even though this is discrete, we want to start thinking about this as though it's a density curve. So we want to say, what's the probability that we would get our result, or one more extreme? So further down into the tail, depending on what side of the mean we're on. And so 57 out of 80 is on the low end of 82. So we want to say not what's the probability that x is 57, But instead, we want to say what's the probability that x is less than or equal to 57. And so that means we're doing a binomial CDF with 57 as our x. All right, and so that is about 1% chance. All right, so there's only about a 1% chance probability that of getting 57 or fewer seniors out of the 80 who say they're planning on going to college if the true proportion of seniors attending college is 82%. So that tells us that we can call into question the district's claim of 82%. So, if 82% of the seniors are going to prom, the probability that we would ask 80 seniors if they're going to college, if they say 82% of seniors are going to college, and when we asked 80, what's the probability that 57 or fewer would say they're going to college? And that is really low. That probability of about 1% tells us the true proportion is probably not 82%, but probably closer to the proportion that we got. So it's probably lower. All right, so now let's think about, could we use a normal approximation for this situation? And so the first thing we want to check is n times p greater than 10? And is n times 1 minus p greater than 10? And yes, both of those work. And so we could approximate this answer using a normal distribution. So we would calculate our mean and our standard deviations using the formulas for binomial random variables. And so we're looking at a normal curve here, the mean of which is 65.6, and we're looking at 57. And we're shading to the left. So we want to know what's the probability we'd get 57 or more extreme out of our 80. And so we could do a z-score or use a normal CDF. And you could see that the numbers aren't exactly the same as our binomial situation, but in both cases, we're going to definitely result in the same sort of calling into question the district's claim of 82% of students going to college. All right, so here is the homework. And so there are 3 problems in this set that require you to use your 3-step process. So, here on number 91, just part C requires a 3-step. So I'm saying 91 is a 3-stepper, but it's not all of the parts. Just part C of 91 requires 3 steps. And then 77 and 79 also require your 3 steps. So make sure that you're doing those in the 3-step process.